Welcome to Advanced Strength of Materials. I'll be covering the summary of the elasticity equation again, and we'll be applying this concept to some problems that we can solve using these concepts. So what is the goal of this course? When you design systems, whether they're mechanical engineering applications like automotive or civil engineer considerations like bridges, or aerospace systems like structural vehicles that fly in space, like aircraft, launch vehicles, and spacecraft. The goal is to design a system that can survive those environments, whatever the environments may be. For an automotive, one of the most complicated conditions is impact damage or impact crash events. But whatever it is, what you want to do is design an optimal structure that have can meet the requirements for the design and can meet the mission specifications of the design, and yet it doesn't fail in service in a way that, for example, in an auto will be so it doesn't injure the passengers, for example. And so that's why it's so important to understand the elasticity equations, which are quite important in design. So we covered that there are three governing equations. So you can see here there's three governing equations. These equations were derived from Newton's law. And from there, we also discussed that there's six strain displacement relationships, which you can see here at the bottom. There's six of them here. And then we have six stress strain relationships, which relate stress to strain. As you can see, there's 15 equations. And the unknowns are going to be the deflections U, V, and W. And if I can solve for U, V, and W, then I can solve for strains. And if I can solve for strains, I can then solve for stresses because stress is equal to the constitutive law times strain. And so we basically want to be able to solve these equations, and they're highly coupled for a lot of different problems. But for some problems, it's easier to solve than others. The boundary conditions are very simple. You either specify deflections on the surface of the body of the material, or you apply traction loads like what we discussed in class. For example, these traction loads don't have to be exactly normal to the surface. They can be like a frictional force on that surface, or it could be a pressure load on that surface, but it could be a combination of the two, which could mean that there's an angle to the normal to the surface. It doesn't have to be always aligned to the normal necessarily. And so what is the goal is to solve these equations, and there's a mistake here. It should be six strain deflection relationships. What we want to really do is to solve these equations for a complicated system, and then I can, whatever the stress is critical, maybe I can thicken it up so that it doesn't exceed the strength of the material. But that is a goal, and hand calculations are also possible for simple geometries, which is the purpose of the next several lectures. While finite elements may be a great thing, the issue is that you cannot model every hole of a composite system, for example, or metallic ring. It may be too, I mean, maybe you can, but maybe you can just extract the loads far away of the area of interest and then use that to build confidence. So hand calculations is really possible for simple geometries. So if you were to use a finite element model, you're going to have a whole aircraft, say. The aircraft, you can develop a model that, based on the CAD model, you can apply the loads, you can apply the boundary conditions, apply the material properties. For example, you may have aluminum, you may have Inconel, you may have different types of materials in the system. So you model that, and that's your structural analysis that you perform. But while fuselage windows can be modeled with great detail, there might be problems modeling rivets and things like that. And for that reason, a lot of times what you do is you create a model like this that can give you a lot of the details of where the structural system could fail. And you do that by interpreting the results that come out of this model. So this model is going to produce stresses, strains, deflections, and you want to make sure that you don't fail the system because of exceeding those structural loads and things like that. So interpreting the results becomes quite important. The other thing you want to do is to then figure out if the rivets could fail, if there's special features that can fail. And typically for those, we use more like hand calculations. And that's kind of like what we want to touch next, just by going through some examples on how that can be done. So here I show a diagram from our book, and what you see here is 5 general things we're looking at, right? So you apply external loads, which is these loads that could be lift or drag or some gravity condition or landing event, for example. So those are your external loads. What we do know is that internal loads are equilibrated with external loads, and that's called equilibrium. And the internal loads must be those stresses that we've been talking about. Those stresses are connected to those internal loads, as we had discussed. And then the stresses are connected to the strains, which is done through the constitutive law. And then the strains are connected to the deflections through the strain deflection relationship. So the goal of this is kind of show you how things are interrelated with each other and how we can use this map to figure out how to solve the problem. So why don't we go in and look at the first problem of interest? So here's an application problem. I have a structural system, a solid system. This example is from my book. So I have the solid system here. It's in solid. And I'm going to assume that at the top surface, y equals plus h, that at this black surface here that you can see, that at that surface, you can slide. So this box can slide across this. At the same time, at y equals minus h, I'm going to assume that this box can also slide or expand or contract. On these lateral surfaces, I'm going to apply a load of P naught so that I'm compressing that structure in that plane, in the x plane. So the surface perpendicular to the x plane. And on the side view, so that's the front view. On the side view, I'm not going to apply anything to that, but I'll let it slide on the top and bottom surfaces. So the question becomes, what are the stresses and what are the deflections due to these loads applied? We're also going to assume that there's no body forces. So there's no gravity on this and we don't have to worry about it. So how do you go about solving this? So we have the strain deflection relationships, we have the equilibrium equations, and we have how strain and strain are related. We also have the boundary conditions, right? So we could start with the fact that it's frictionless at the boundary. And because it's frictionless, what I'm going to say is that the deflection does not depend on y and z. It's going to just depend on x. So let's look at that assumption carefully. U, V, and W are the corresponding deflections at every point in this body in the X, Y, and Z correspondingly. So for example, U is the deflection in the X direction, while V is a deflection in the Y direction. Now here is written that the block is constrained to 0 deflections at all points in the Y direction, but is free to displace in the Z direction. So what is that telling us? What this is telling us then is that this vertical deflection is likely going to be 0 because it's fixed at the top and it's fixed at the bottom in the Y direction, and V is the deflection in the Y direction. So that makes total sense. So we're going to look at the deflection then, U, which is the direction, is in the X direction, and we're going to look at the deflection in the Z direction, which is the one that you can see here, out of the plane of this page. So when I look at the deflection U, and that's this one here, it only depends on X. That's a very good assumption because the load prescribed, that pressure is uniform. The deflection is, what we're saying is that it does not depend on the value of X. It depends on the value of X. So the deflection U, this deflection U, depends on the value X, but does not depend on Y and Z. Meaning that if I look at the deflection of this point, if that move is 0.1 inch, which clearly doesn't. I mean, you'll see here that the center line should stay in the center. Kind of makes sense. But if I look at the deflection, say here, and that moved 0.1 inch inward due to the pressure applied, what we're saying is that the deflection here, 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 that all of them are likely to move 0.1 inch in the X direction. Also, so it does not depend on Y, and it does not depend on Z, meaning the deflections are uniform through the thickness of that solid plate. I'll continue saying that W, the deflection in the Z direction, which is out of the page here. So in the left side, the front view, the Z axis is out of the page. So what we're saying is that the deflection W only depends on Z. So it does not depend on Y. So the deflection is the same at this point, at this point, at this point, at this point in the Z direction. And so that's an assumption, but it's a reasonable assumption given the problem statement that this block is free to expand, but it cannot move in the Y direction. So I can use the strain deflection relationships. Given these deflections that we know of the system, I can use the strain deflection relationships to calculate the 6 strains that we know of. And we know there's 6 strains. Epsilon xx is partial u respect to x. Epsilon 2 is 0 because the derivative of v respect to y is 0. Epsilon 3 is epsilon zz, which is partial w respect to z. That's also unknown. And then there's no shear strains because you can see quickly that if I were to evaluate, for example, let's evaluate twice epsilon yz. That's the partial of v respect to z plus partial w respect to y. And you can see here that v is 0. So that goes here, that gives you 0. While w is not a function of z, of y. So it's partial w, but w only depends on z, not y. So that's 0 also. And if I try that with each of the other strains, I did this one, but if you tried it with this one and this one, you'll get the same answer. And this is just a strict definition. We used the fact that epsilon xx equals partial u respect to x. And I'm using this quantity here, so that becomes a partial small u respect to x. So all I've done is use the strain deflection relationships to get there. And then I can use the constitutive law. We know the stress, and this doesn't have to be memorized, but this is the stress field. And I'm using a different convention, but I don't want you to lose sight of the fact that this is sigma xx, this is sigma yy, this is sigma zz, sigma yz, sigma xz, and sigma xy. It's the same thing. And then we showed that from here, this page, that they're all pretty much 0. You can see here, let me clean this up. You can see that the only non-zero terms are this one and this one. Everything else is 0 based on the assumptions we made. And so when you go here, those are the only 2 I have. So if I multiply this matrix times this vector here in the right-hand side, what I get is something that looks like this. And I invite you to try to, in the comfort of your home, to see if you get the same answer. But I think you will get the same answer. So SXX is found like this. SYY is the one there. SZZ is there. And the shear strains are 0, which kind of makes sense. If I apply compression load to this surface here and this surface here uniformly, and I have a square here, I don't expect the square to distort suddenly for an isotropic material. It doesn't seem to make sense. It seems like the angle change is unlikely to occur. So it's unlikely that this square is going to experience an angle change like that, given the loading environments I have. So that makes sense. I'm getting that the shear stresses are 0 and that the shear strains here are 0. That makes a lot of sense. So I can use the equilibrium equations. Since the shear stresses are 0, that's 0, that's 0. There's no body forces. That's 0, that's 0, that's 0. There's no body forces or shear stresses. That's 0, that's 0, and there's no body forces. In addition to that, we know, as you know from here, these equations, that I have the calculations for SXX, SYY, and SEZ. So I can use that information. So what do you get then for from the first equation? I get this, which means that SXX is a constant if I integrate this by x. So for example, I have SXX dx equals 0. Well, what I can do is I can integrate that, and that gives me a constant. So the integral of 0 is a constant. So you can see here, that's why I have that. That has to be 0, so that's constant. And that has to be 0, so the integral of that has to be a constant. And the question becomes, okay, well, fine. How do I find that constant then? How do I do that? And notice here that these constants depend on y and z for this one, depends on xz for this one, and depends on xy on this one, because I integrated about the z. Therefore the constant can vary, depend on x and y. And for the integral about y, with respect to y, tells me that the constant can be a function of x and z, which makes total sense, and so forth. So how do I find these constants that I have here? So I can use the boundary conditions. I haven't really used the boundary conditions. If you notice here, I haven't used the fact that these boundary conditions are known. Like, for example, I know this boundary condition there. For example, this one here. Let's examine, for example, this one. At this boundary, let's examine that. I have what? I have sigma xx at x equals a, because the length there is a. So at this boundary here, I must have the sigma xx equals minus p naught. Just by using Cauchy's relationship, you can check that. Yeah, I mean, I can show you that. Let's do it quick so you can see that. So what is Cauchy's formula say? Cauchy says that on the surface of the body, the traction is T1, T2, or we can use letters like we've been doing here, X, Y, Z. And I have the stress field here. And on that surface here, I know what I have, but I also know that I know the normal NX, NY, and NZ. So what do I have? I have that the load applied is minus P naught 0, 0, something times the fact that I have a normal to this surface, the normal to this surface, that end there, that's not normal. That normal here in hat is 1, 0, 0. If you multiply, and this will be sigma xx, sigma xy, sigma xz, etc. I won't do all of it, but what you find is exactly what if you multiply this whole thing, what you find is this equation, that sigma xx must be equal to minus p naught at that boundary. Not just that, you find that sigma xy and sigma xz must be 0 at this boundary, which makes total sense, right? It has to make sense. I can then check what it will be in this boundary and each of these boundaries. So if you do that experiment, that's how I can find these constants, is by looking at the boundary conditions. And you will see that we'll be doing that quite a bit. So I already showed you that at the boundary, sigma xx equals p naught. I'm using SXX here in my book, but that's equivalent to the stress sigma XX. So that's fine. That's what I'm using in my PowerPoint, going back and forth. I think it's a good idea to be looking at different ways of writing things. So you can see a boundary X equals A, right? At that boundary, SXX has to be minus P naught. But I told you already that SXX is a constant, which tells you the C1 has to be P naught, minus P naught. So the stress is uniform, is what this is telling us. Further, SZZ is 0. Why is that? At Z equals B. Let's look at that carefully. So I examine why sigma XX equals P naught at X equals A. But why don't we examine what it will be at the following boundary? Let me show you what I'm talking about. Give me a second. Let's erase this so that it's not cluttered and we can kind of follow what's going on here. So let's look at that boundary, right? So that boundary that I'm talking about is this one. Because solid material has 6 phases, right? So this phase here at Z equals B, there's no traction loads applied, 0. So the traction on that surface is 0, 0, 0. What is it normal to this surface? Well, I need to figure out what the n hat vector is. In this example, it will be 0, 0, 1. And when you do these calculations, you'll find, so this is sigma xz. Right, type this here. Sigma xz, sigma yz, and sigma zz. I'm not going to type the rest of it because that's the one that's going to only matter. When you multiply these two things, you will find that sigma zz is 0 at this boundary that we're looking at. Also the shear stresses too. And so that's why I wrote that SZZ, and this is an example from my book, but it's worth going through it. And that's why SZZ, the stress in the Z direction is 0 because of that boundary condition. And C3 is 0 as a consequence. So, okay, so I impose the boundary conditions on the X phase and Z phase. I also have the SYY equation that's a constant. And the question is, what is that constant, right? Well, so let's look at SZZ carefully. So I have SZZ, the formula for SZZ. How do I find that formula? Well, that came from here. So what I can do, I can multiply SZZ is this one. I can multiply that row times that column to get SCZ, right? And that's how I got this expression here, this one right here. So I'm kind of repeating that equation in the next page, just reminding how I got there. So that's what this one is. But I know SCZ is 0, so I can then solve from here. I can solve for one or the other, right? So I solve for epsilon ZZ, and I get this. So that's interesting. Let's think about what's going on there, physically what's going on there, right? So let's go back to the problem statement. What this is telling us is that if I know what the strain and if I know the Poisson ratio of the material, if I know the strain in this direction, basically what is the length change divided by original length, in that direction, I can tell you what is going to be the strain in out of the page, which is this direction, along the Z direction, out of the page, right? So, and we found the relationship of that. I showed it to you, is right here. Epsilon ZZ equals the minus of this, right? So, epsilon ZZ is minus of this. So In other words, if I know the Poisson ratio, I can tell you exactly what the strain will be out of the pitch because of the AZZ direction. The stress in that direction is 0. You can then go to your first equation. So we know the first equation very well. We know the first equation from here. I know this equation, SXX, but I also know that SXS is P naught minus P naught and it's constant. So I can make this equal to minus P naught. I can solve for epsilon ZZ out of this equation, or I did it out of this equation because this is equal to 0, the whole thing. So I can solve for epsilon ZZ, plug in what epsilon ZZ is in here, and then solve for epsilon XX. So that's what I'm trying to do, solve these two equations in stars simultaneously. And I did that for you. So I took this equation that came from SCZ, constitutive law, plugged it in here, and then I know that this is equal to minus P naught. So I solve for E epsilon XX, which is the strain in the X direction. And when I do that, I get something very simple, which looks like this. So that's the strain in that direction. I can also calculate the strain in the Z direction. So once I know epsilon XX, I can plug it back in here and calculate the strain in the Z direction. You can see it there. Okay, so you may ask me, well, what is the strain in the Z? What is the strain in the Y direction, right? I didn't cover that. Well, I didn't because we assumed that the deflection in the Y direction is 0. So in this direction, we're assuming that the deflection is 0. And the reason is because the block is constrained at the top and the bottom. So for that reason, epsilon YY will be 0 because that's a partial of V respect to Y. And I showed you that in our assumptions, V was 0. So that's why that's not being discussed. And then it turns out that once you have all that, since you know epsilon XX and you know epsilon ZZ from the previous two equations, this one and this one, I was able to solve it for that. I can actually calculate then the stress in the Y direction, which actually there will be a stress due to that. So the stress in the Y direction turns out to be minus nu times P naught. It actually simplifies to that. And that stress is constant throughout that block. Because I found epsilon XX, right? I solved for that. I know epsilon ZZ because I know epsilon ZZ depends on epsilon XX, and that came from one of the equations. Then I can calculate stress in the Y direction. So you pretty much know the stresses on that block, and you can predict failure of that block just with the information that was provided here, right? So I had the 3 equilibrium equations, I used the constitutive law, and I use the strain deflection relationships to make that happen. I can then calculate deflections, and that should be very easy. I know what the strain is because I found it earlier. That strain was this much, and the partial u respect to x is this much. Well, all you have to do is integrate this respect to x, and if I do that, I get u, the deflection on the left-hand side, is equal to the integral of that, which is going to have p naught x plus some function. Okay, and so the deflection becomes this, and this goes to 0 if you impose boundary conditions, and I'll explain what those boundary conditions are. Similarly, you can find the deflection in the W direction, in the Z direction. The deflection in the Z direction, again, the strain in the Z direction is this. I can integrate this with respect to Z, and then that'll give me W equals that. And then this goes to 0, and I can explain why F1 and H1 is 0. You can find that by, for example, I could say, okay, the deflection U is 0 at x equals 0. Because if x is 0, I can say the deflection is 0 at that point. Okay, let me say why. So if I'm applying a load uniformly, laterally to this block, I'm going to say that very likely the center line will stay untouched. It's not going to move left or right. So I'm going to say that the deflection U at that location is 0. And that's true for every point here, actually. So I can make this into Y. So if I plug in, and let me clean this up so it doesn't look cluttered. So if it said the deflection U is 0 at the center line, you can see quickly that all I get is F1. So F1 is 0 and it goes away. And the same thing with H1. So in this problem, what I covered was the ability to determine stresses, strain, deflections, using the concepts that we already learned throughout this body of material. Let's move to example 2. A new example. In example 2, I'm given a cylinder of material, and that cylinder has a wall thickness T, length L, diameter D, and this cylinder is getting compressed by a load P. Okay, so what is that's what this problem is, and the question being asked is what is the length, the change in length L due to that load P applied, the change in diameter D, and the change in volume of this cylinder. Well, one of the things we're going to require is if I apply a load to cross section that has cross sectional area A, I can calculate stress. And so,
Thank you.
okay, so then I want to do that. So how to calculate the area, because that's going to become important. So one way to do it for thin vessels, you can calculate the area that's shaded there by taking the mean diameter basically. But it's so thin anyway that you can just say that the perimeter is pi d, and if you multiply by the thickness, that gives you a very good approximation for area. And I should have used d uppercase. So that's true for thin vessels. You can just use that formula, pi dt that you see there. So very good for thin vessels, and it works well. So what does the applied load tell me? So I have a load applied. I have a load applied P in compression, so it's a negative sign. I divide it by the area. So I have P divided by pi dt. So that's easy. That's what I just derived right now. So that area is pi dt, the shaded area there. And so that's just an assumption that's a thin vessel. If it's not thin, then you have to divide it by the actual area, and that's going to be just pi outer diameter squared minus pi inner diameter squared. But that area is approximately equal to pi dt for thin walls. So it's kind of nice to use these simple formulas so you can kind of do the calculation quicker. So because you know that the other stress components are 0, obviously if I'm applying a compression load to this tube, you can quickly see here that sigma yy is 0. I'm not applying anything there. Sigma zz is 0. I'm not applying anything in that direction. And all the shear stresses, sigma xy, sigma xz, and sigma yz are 0. There's no shear stresses applied. So because of that, I can use the constitutive law, right? And so what is the constitutive law? So let's look at that. So I know that all the other stresses are 0. This is the only one that's non-zero, and that's going to be equal to P divided by pi dt, but these other ones are 0. For this particular problem of a cylinder under compression load, right? If you invert this relationship, what you get is that these three are 0, and that these three are the ones shown here in the bottom here. Now that makes a lot of sense. Let's examine that. I have a cylinder with a load applied P. And this cylinder will compress in the X direction. So that's the X direction. And it's going to compress by a strain amount of epsilon xx, which is sigma xx divided by E. But I expect that laterally, I already discussed this, that this cylinder should contract, and it contracts by a Poisson ratio times epsilon xx. So if you recall, we said that epsilon yy will be equal to minus nu epsilon xx. But I already know what epsilon xx is sigma xx divided by E. The same thing applies to epsilon zz, but I won't repeat it. So again, all that comes from the constitutive law I draw here, the one I'm showing here. That's what you will use to solve for epsilon xx, epsilon yy, and epsilon zz. So what is the change in length? We already discussed it. So epsilon xx equals change in length divided by L of that cylinder. Well, I know the original length of that cylinder is L. I know epsilon xx because I already calculated that just a second ago. So then I can calculate change in length. Well, change in length is equal epsilon xx times L. But I know that epsilon xx is also sigma xx divided by E. And I know what sigma xx is because I know what it is from here. And if I multiply this by L, this strain here, multiplied by L, then I get the change in length. Because epsilon xx is equal to delta L divided by L. So I can calculate the change in length using this formula. So the next question becomes, how you calculate the change in diameter? Well, we know that when we compress a structure, it's going to expand in the other direction, right? We know that. So we know that epsilon yy is going to be the minus nu of epsilon xx. Well, that should be an easy thing for us to figure out. We know that this is minus nu times epsilon xx, which I already calculated earlier without the L, obviously. So that's P pi dt E. Okay. So what is the change in diameter? Is going to be epsilon yy times the diameter, which becomes, this becomes plus, because there's a minus there, and there's a minus here, that becomes a plus. And so this multiplication here gives me P times nu pi TE, which is what you see there. And then how you calculate the change in volume, something isn't showing up right, but we're looking for delta V divided by V. And we discussed that can be found as a summation of the trace of the strain tensor. And I already showed you that epsilon xx is this much, epsilon yy is this much, epsilon zz is this much. Just add them up, and when you do, you get this expression. Now there's an error here, which we'll fix. Sigma xx, I just factor sigma xx out of this equation. So that's what this is. And let me find what that was. That was pi divided by P divided by pi dt. P divided by pi dt. So that this should have been a pi. I apologize. So that's the change in volume due to compressing that cylinder in this application. So what this problem covered, this problem was looking at a cylinder that's compressed, and the question was to change, find the change in length, the change in diameter, and the change in volume. It turns out that it's possible to calculate the strains, the deflections, and the stresses. Let's look at example number 3. So in this example, I have some sort of prismatic bar. So that's your bar here. And that bar is fixed on that red shaded area that I just showed you. And my goal here is to determine what the self-weight is doing to the system. So there's a self-weight. So the weight of that column can stretch this material. So you know that the body forces then are going to be such that Fz equals minus rho g, where rho is the material mass density and g is acceleration. So we're going to assume that the cross-section has uniform tension and that it produces a weight due to the lower portion of the bar, and we need to figure out what that is. You can see here that the stresses should be 0, like all other stresses should be 0. And the only one that should matter is the one in the z direction, because that's the one pointed this way. And thus I expect that that's the only stress that really matters because of the self-weight in the z direction. So I can apply equilibrium equations. If you look at the equilibrium equations, so you have what? Partial sigma xx respect to x as an example. So there's no stresses in the other directions. The only stress that you should develop is this one. So what do I have? There's 0, there's 0, that's 0, that's 0, right? So the only one that really is going to show up is going to be but the shear stress is 0. So the only thing you really get is this term, which is that, and the body force term, which is that. I put this in the other side. But the body force is minus rho g because it's a body force. And so that's what you see there. Now I can easily integrate this equation with respect to z, so I can get this expression for stress. So what is that telling us? It's telling us that the stress is going to be higher, as I go up in this prismatic bar. For example, at z equals 0, the stress of a little piece here is going to be 0. Obviously, it doesn't experience any self-weight, right? But it's saying that at z equals L, that stress over here is going to be much larger because you have all this weight below it pulling it downwards. So it does make sense. This equation does make sense to me. So the stress field is given by this. Well, what can I do with that stress field? I can go back to the constitutive law, right? We already discussed the constitutive law. I can write it here for you one more time so you can remember it. We learned that this is 1 over E minus nu over E minus nu over E, 1 over E minus nu over E 1 over E. And then there's more terms there. Sigma XX, sigma YY, sigma ZZ, etc. When you multiply this equation times this equation, which is the constitutive law multiplied by the stress field, you'll quickly find that the strains that you get are the ones here. It makes total sense that the shear strains are 0 because there's no shear stresses. And this also makes a lot of sense. This one makes a lot of sense. Why? Because if I'm pulling the material downwards due to self-weight, you expect that here on this edge, this is going to contract in that direction because I'm pulling the material downwards due to self-weight. So that's where the Poisson ratio is showing up on epsilon XX and epsilon YY. That Poisson ratio is showing up. Very interestingly, I can draw what this would look like. For example, at Z equals L, I have the most strain. So what I expect this material to do is going to stretch. This point is going to stretch a lot. So I think it's going to look like this. When it loads up due to self-weight. You can see that because it's contracting a lot. Right? And so you're going to have contraction due to that thing stretching downwards, the block stretching downwards. Now you can calculate the deflections too. How do I do that? Well, we can take this example here, epsilon XX. Let's try that. So let's try that. Epsilon XX is minus nu rho GC divided by E. Well, so if this is also partial U with respect to X, right? Because that's the definition of strain in that direction. So I could integrate this equation with respect to X on both sides. So I get U is equal to minus nu rho GC divided by E times X plus a constant. And so that's why I get this deflection there. I can calculate that constants because I know that the bar is affixed at the top. So you can actually do some calculations to figure that out. And then you can calculate V, and then you can also calculate the vertical deflection using the same procedure I just showed you. So with that, that shows how to apply some closed, how to apply elasticity to simple closed form solutions that are manageable.